This is your video to go with Super Mario Parametric Plumbers, and here we have Mario in the plumbing here. Um, so let's talk about why we're watching Super Mario. Look at Mario jump right now, completely vertical. It takes him some time to jump, and he's going straight up in the air. This is why we're doing this with parametrics, because Mario can go straight up. He can walk straight forward, or he can have a combination of forward distance and upward height. So this fits well with our parametrics unit. As he jumps, watch the shape that he makes. Okay, in this part, he just has X over time, right? There's no height there. Now he has height and no forward movement. So separating it into X over time and Y over time works well. Look at him jump now. As he has forward velocity as well as upward velocity, what function shape is he making? Let's see if we'll have a better one here in a minute. Okay, right there. And see that, hopefully you're realizing that he's making a parabola shape when he jumps. There they are. Nice, good parabolic shapes that he's making. And so as Mario jumps, a lot of the times we'll be seeing parabolas and having equations of parabolas. Okay, Mario, go away. There we go. Okay, so how does this affect us in our homework? I'm actually going to do number 6 from your homework with you, number 6. So, because it's probably one of the harder ones, so let's do that one together, and then you should be able to go back and do the easier ones. So number 6 says, Emily is a programmer working on the new Super Mario Brothers game from Nintendo. The game designer tells Emily when Luigi jumps, so we got Luigi instead of Mario, his maximum height needs to be 9 feet above the ground, and he needs to stay in the air for 3 seconds. And his maximum forward speed is 6 feet per second. Okay, so we're going to write parametric equations describing Luigi's height and distance as a function of time. So here we go. We have x of Luigi over time. I'm not sure if you have that t there, but in function notation would have a t to show that we're doing x over time. So what did he say, x direction? It looks like he's going 6 feet per second. So since we know rate times time equals the distance, so the rate is 6 per second, and so t for time for seconds there. Okay. What about Luigi's height and distance as a function of time? Luigi's distance. We've done the distance, so let's do height now. Okay. So what did they tell us about the height? Well, he's got to be 9 feet above the ground, and he's got to stay in the air for 3 seconds. 9 feet above the ground, and he's got to stay in the air for 3 seconds. So let's think this through here. Let me do a little graph. Okay, so let's use, and this is not distance on this x-axis, it's going to be time, since they're just telling us we're separating it. Our distance isn't even part of this parametric for our y. So time there, and it says he needs to be in the air for 3 seconds. So here he is. This is going to be second 0, 1, 2, and 3 seconds. So he'd be back in the ground, right? If he's in the air for 3 seconds, he'd be back on the ground after the 3 seconds. And then, which makes sense on a parabola, that halfway through he'd reach his maximum height, which we said we wanted to be 9. So I'm just going to come up here and call this 9 feet. So halfway, half of 3 is 1.5. Let's record that. Okay, so this is not really showing the shape of his jump, even though most of the time if he is moving forward, it isn't a parabolic shape. This is really just his height over time. Okay, let's write height. Okay, so we need to come up with the equation that would give us that graph. So obviously it's going to be quadratic, and what we learned from our warm-up is how to get an equation with 3 points. So, you know, if we wanted to do this tabularly, you might rather have a table instead of a graph. We'd have the 0. This is our time, and our height, which is our y value here. At time 0, he would be a height of 0. At time 3, he'd be a height of 0. And then halfway between there, or 1.5, he would be 9 feet tall. So if we talk about it, look like that, we can tell this is the vertex, right? Put it on this side. We have our vertex there. So let's come over here and get started. Y equals A. Well, I'm not sure what A is right now, but let's do T. Don't forget to put a T there. It's really tempting to put an X because that's what we're used to. Minus, let's put our 1.5 squared plus 9. Now, what we figured out yesterday is that our A is rise over the run squared. Rise over the run squared. So what's rise in this case? In this case, rise is not just 9, it's actually -9, right? Because we technically, it's a downward opening parabola. So -9. Divide that by the run, 1.5, but we do have to square that. So punch that in your calculator to make it look pretty. Rise over the run squared, and I think it's going to reduce down to actually -4. So that's nice. So our A value is going to be -4. Let's go back and put that here. In fact, let's just put it right here. So -4 T minus 1.5 squared plus 9. So there we have our set of parametric equations for Luigi. Okay, easy enough. Let's go to 6B. That was 6A, if you're wondering. 6A. Let's look at 6B. 6B is an albatross is chasing Luigi. I haven't played this game ever, so I don't know about an albatross chasing Luigi, but here he is. An albatross is chasing Luigi while flying at a height of 12. Okay, right there I know height of 12. Height is going to have something to do with y. A forward speed of -7 feet per second. That sounds odd, doesn't it? -7 feet per second. And a vertical speed of -3 feet per second. The albatross is holding a bomb in its talons, and it drops the bomb when it is 10 feet in front of Luigi. Write the bomb equations which describe the bomb's height and distance as a function of time. Bombs have mass, so gravity does affect. Okay, well, that's going to be interesting. Well, let's get this set up. So this is x of the bomb over time and y of the bomb over time. Okay, so even though this doesn't really make sense in our head, let's think this through. What all has to do with x? The bomb drops when it's 10 feet in front of Luigi. 10 feet in front. This bomb is actually moving backwards, so which is kind of odd, but 10 feet in front of Luigi, and then has a forward speed of -7 feet per second, so -7 every time. So there we have our x movement of the bomb. Let's talk about y. So to do y, you have to kind of go back to some of the things you may have done in physics, but if you remember, y equals, and then we have 1/2 times gravity over, you know what, let's put x over here. We will have to put time over there, t, but let's put an x here. And then you add your velocity, and then you add your starting height. So VO means the velocity at time 0, or initial velocity times, I did time again. We'll put x for now. And then initial height. So here's some things we know. It told us the initial height was 12, so we know we're going to put a 12 here. And velocity, what did it say about the velocity? And it drops the bomb a vertical speed of -3 feet per second. So that's your velocity. It's going down 3 feet per second. Now, let's talk about gravity. Yeah, when you do gravity, and you've probably done this in your science classes, but gravity, you have two things. So gravity of feet per second is we put 32 feet per second, and it's negative, so it's coming downward. Gravity's always going towards the Earth. So we end up with, I guess our negative would be on the 1/2 there, and we multiply negative 1/2 times 32 feet per second, so you end up with the negative 16 you may have seen before. And then if you do in meters per second, it's 9.8, so you do the half of that, and you get 4.9 in your equations. You may recognize those values of being something you've used before. But we're not on Earth. We're in Mario land, and so what we'll use here is, and the good thing is, the bomb and Mario are in the same universe, whatever that is, and they have, or I shouldn't say universe, in the same environment, and so they have the same gravity pulling on them. So if we look back up, the A value for Mario right here is a -4. So that implies our A value should be -4, which since that is gravity for the bomb as well as for Mario. So we're going to end up with all of this just becoming a -4. So long story short, what you need to know is for your A value of the bomb, it's always going to be the same A value as Mario because they're in the same place. So the gravity would have an equivalent effect on both the bomb as it does on Mario. So just kind of steal your A value from Mario or Luigi, whichever character you're using at the time. Steal that A value, and then the question will always give you your initial velocity and your height. Now, on the velocity thing, if something is dropped, not pushed, or it doesn't tell you an initial velocity, then it would just be 0. When you drop something, it doesn't have an initial velocity. When you throw something, then it would have a velocity. You throw it up, it'd have a positive. Throw it down, it'd have negative. So if it just says it drops, then it doesn't have an initial velocity. It would be 0. 0 times x, so you just wouldn't have that linear term in your equation. Okay, so we're going to transfer it up here, and we're going to have to change our x's to time. So -4t squared minus 3t plus the height that started is 12. So there we are. We have another set of parametric equations, and that it will be Luigi and the bomb together. So 6c is going to ask you, 6c, will Luigi get hit by the bomb? Why or why not? So this is going to go just like the ships. We want to see if they're at the same horizontal, same vertical at the same time. Same horizontal, same vertical at the same time. So, well, that's easy enough. So here we go. Let's take our x's. We know, let's see, what was Luigi's x? 6t. So 6t should equal the bomb's x value, which is 10 minus 7t. So we're going to end up with 13t equals 10. T equals 10/13, which is about 0.769 for your time. So the way I like to do this is I actually will write all my equations again and plug that t value in. I'm going to actually go up and retrieve mine so I don't have to. Whoops, not like that. Let's group these together. And I'm going to copy those. Go down and actually put them down here where I can see them. Okay, so you might just want to copy yours again down, or I guess you could go back up where they are. So there is Luigi. So what I'm going to do is I'm just going to plug in, let me do it in a different color so you can see, 6 times the time, 0.769, and he's going to be at 4.615. so to the right of the starting point at time 0. And let's plug in a t here, so it's going to be negative 4.769 minus 1.5 squared plus 9. Good idea, by the way, to store your t, store your 0.769, the long version of that, as t, and then you can just plug it into all these equations and just push t instead of having to repeat that long decimal. Okay, so we're going to get 6. Let's see, 6 point, I can't tell my handwriting if that's an 8 or a 9. 864, we're going to say 6.864. I'm actually going to move that right up here. Okay, so now we know where Luigi is going to be. Let's find out where the bomb is going to be. So let me go back and grab this equation. Let's take this down, and on my paper I would normally probably put it beside, but I don't have room here, so let's put it underneath. Okay, so again, I'm taking my time of it's 0.769 and plugging it in. So it's 10 minus 7 times 0.769, and so the bomb is going to be at 4.615. We know that works because we found the t that would make that work. But when we plug in the 0.769 here and the 0.769 here and plug all that in, we get 7.325. Okay, so this one's actually a little bit hard, because they are pretty darn close, aren't they? They're not exactly the same. So my ordered pair here is 4.615, 6.864, and the one down here is 4.615, 7.325. So, you know, it might not hit on his midsection, but we're probably taking out some limbs or so. So, you know, as long as your sentence is good, my sentence here was the bomb will probably hit Luigi because at time t.076 seconds, they are almost at the same place. They are both 4.615 in the x direction, even though their y coordinates are a little off. They're off by 0.461. The bomb is higher and Luigi is more than 0.461 feet tall. So he's probably going to get hit, even though they're not dead on. So let's look at that. I have a neat little thing. And you can put those in your calculator and put the parametrics in your calculator and actually watch. But I have one that's a little bit more exciting. Let's look at that. Okay, so here's a sketchpad animation of our scenario. And we have a time. Notice my table here I've got 0, 0, 1.59, and 3.00. The speed is 6, I believe was what we had said. And the start, see how the start is 10, 12, which were the two numbers we had, 10 and 12 for the 10 feet horizontally and 12 feet high. And then we have the horizontal speed at -7 and the vertical speed at 3. Now, to warn you, my people that are very particular out there, this may not hit because we are close, but not exactly on. So don't hold it against me if the fireball doesn't, the bomb doesn't actually hit Luigi. So here we go. Let's animate and look at this. It says fireball, but I think that it's really a bomb. So we just can't change that word from fireball to bomb. So let's watch this go. Okay. Actually, I just paused my video making, and I noticed that I had put that in fireball instead of bomb. So notice I've zeroed out the fireball. We don't have a fireball in this scenario. but we do have a bomb. And now I have put the start in the bomb and the horizontal and vertical speed into the correct locations now. So let's animate this now and see what happens. Are we ready? So here's the bomb in front of Luigi, and this is here we go. Let's see what happens. Oh, it went right through him. It did hit him. So there we go. Let's reset just to look at that one more time. Boom. There we go. Okay, that's a little more fun than your calculator, but you're going to have to just use your calculator most of the time if you want to watch these go. So now you're ready for your homework for 1 through 5. We've got number 6 done.